name is HIDEKO NOMURA from Tokyo Tech, and first of all, I would like to thank the organizers to give me opportunity to introduce our recent work in this interesting conference. Today, I would like to talk about our work on modeling chemical reactions and formation of complex organic molecules in protoplanetary disks, and also our recent ALMA observations of molecular lines toward protoplanetary disks. In this talk, I will mainly introduce these two papers, the result of these two papers. First, thanks to the recent development of infrared and sub-millimeter telescopes, we are now getting detailed information of the protoplanetary disks. These figures are the infrared and ALMA observations of protoplanetary disks, and now we can get detailed structure not only in the dust component, but also in the gaseous component, thanks to the ALMA. So now we get information of detailed physical and chemical structure of planet-forming region in the disks. This figure shows a schematic view of the chemical structure in protoplanetary disks, and protoplanetary disks is mainly heated by the central star, so outer region of the disk is cold, and molecules and gaseous component frozen out on the grains, and in these icy mantles, more complex molecules are formed due to the grain surface reactions. On the other hand, in the inner region of the disk, the temperature is high, so this icy mantle molecules evaporate into the gas. In addition to it, the surface layer of the disk is irradiated by UV and X-rays from the central star, so these regions are affected by the irradiation of this kind of non-thermal irradiation of the central star. And if we look at the solar system, we can see that, for example, in the comet, we see these kind of the relatively complex molecular species which are formed on the icy grains inside the comets and heated when the comet close to the central star and evaporated into the gas. So we are interested in the connection between these protoplanetary disks and the solar system and other exoplanetary systems. So far, these are a part of the molecules discovered in interstellar medium, as we have seen in these morning sessions. And these molecules are complicated among the interstellar molecules in the interstellar medium, and next target of the molecular hunters of the interstellar medium is amino acid. On the other hand, in the case of the solar system, detection of glycine has been reported in stardust missions, and also a lot of amino acids are found in the meteorite. So we are interested in how these complex molecules in our solar system are formed from these relatively simpler molecules found in interstellar medium. In the case of the protoplanetary disk, observationally, it is not very easy to detect complex molecules. It is because the disks around the low mass star is not very luminous, so we can only detect relatively smaller molecules compared with the massive star-forming regions. But thanks to ALMA, the number of these kind of a bit complicated molecules are increasing now. And these are some examples of the observations of relatively complex molecules in protoplanetary disks by ALMA. So the cyclic C3H2 and methyl cyanide is one of the most complex molecules which have been observed toward protoplanetary disks now. But we expect more species and will be observed toward protoplanetary disks by ALMA. So in order to predict how complex molecules can be formed in protoplanetary disks, we first model the physical structure of the disks. And in this model, we take into account the irradiation from the central star and then calculate the gas and dust temperature and density structure. And these figures show the resulting gas temperature and density profiles. And this is the disk radius and disk height, and we can see a variety of physical structure can be found in protoplanetary disks. Now, in the case of the interstellar medium and also protoplanetary disk, we think that complex organic molecules will be formed on dust grains, which is also shown in today's morning talk. In the case of the cold dust grains, molecules and atomic species stick on the grains, and mainly hydrogen can migrate around the dust grains. It is because hydrogen is the most small molecules and can easily move on the grains. And as a result, these kind of saturated molecules can be formed on the grains. And if the dust grain is heated, these molecules are evaporated into gas. And even if it's not heated, if there is a UV or a cosmic ray or X-ray irradiations, in this case, a part of the molecules can be dissolved into the gas. In addition to this process, in order to explain the more unsaturated complex molecules found in the interstellar medium, some another processes of grain surface reactions has been proposed. So if the dust grain is a bit warmer, in this case, relatively heavier molecules can move around on the grain, and as a result, these kind of unsaturated molecules can be formed. So these kind of reactions are recently included in the chemical reaction network, and then we take into account these kind of grain surface reactions and also gas phase reactions together with gas grain interactions, I mean the freeze out and disruption of molecules on and from the grains. And then we performed the chemical reaction calculations of chemical reaction network based on the physical structure we calculated for the protoplanetary disks. And these are some of the results of our calculations. This figure shows the molecular abundances on the grain surfaces, and this is again disk radius and disk height. And we can see that these kind of relatively complex molecules can be formed efficiently on dust grains, not only in the cold regions, but also relatively warm regions. So this is because of the grain surface reactions as I shown before. And if we look at the gas phase abundances, we can see that these molecules can be abundant in these regions. So in these inner regions, these molecules are abundant because it's warm enough so they are summarily evaporate into the gas. But in these regions, disks are cold. Disk is cold, so these molecules are evaporated into the gas because of UV irradiations and also cosmic ray irradiations. And based on these model calculations, we propose the ALMA observations, and we get some result. So this is for the methanol line proposal towards the disks around TW star, TW Hydra. And the methanol line is very weak, so we couldn't detect only one line, but we stuck 3 lines of methanols and then get the detections. We compare the result with the with model calculations, and this figure shows the gray scale shows the model calculations, and white contour shows the observations. If we assume that the molecules are distributed around 30 to 100 AU and relatively low molecular abundances, in this case, we can fit the observations well. If we compare the result with the Herschel observations toward cold H2O disk line, in this case, we find this kind of number of the abundance ratio. This is relatively, this is similar to the abundance of comet, and we think that part of the molecules on the dust grains, I mean part of the methanol and water on the dust grains are dissolved from the grain due to some non-thermal effect. So we think that due to this kind of observations, we can somehow see what kind of molecules can exist on the grain surface in protoplanetary disks. And in addition to these observations, we also observe the carbon monoxide lines towards the same disk with higher spatial resolutions. So in these observations, the spatial resolution is about 20 AU, so we can somehow observe at the radius down to the radius of 10 AU in these observations. So, and using these observations, we derived the CO column densities as a function of the disk radius. And also we observed the dust grain emission, so we also obtained the dust surface density profile as a function of the disk radius. Using these two surface density distributions, we obtained the CO gas to dust mass ratio as a function of the disk radius. The resulting number of this CO gas to dust ratio is very small, more than 2 orders of magnitude smaller than the typical interstellar value. In the case of the outer disk, I mean the outside the CO snow line, it is reasonable we can explain it the CO gas freeze out on the dust grains. But in this in the case of this model, CO snow line is thought to be about 30 AU, and we find the CO gas depletions even inside the CO snow lines. It is possible to explain it by gas depletions, but because HT gas is observed toward this disk, so we think that it's not gas depletions, but depletion of CO gas. So there are some interpretations, but this is one of the interpretations we suggest. If we compare the observations with the model calculations, which include the grain surface reactions, this is the result of model calculations, CO column density as a function of the disk radius. And we can see CO depletions depending on the time in these model calculations. In these model calculations, CO gas is depleted in these regions because CO gas stick on the dust grains and react with another molecules to form more heavier molecules which cannot evaporate from the grain in this temperature range. So these observations of CO gas depletions even inside the snow line could be explained by this kind of formation of larger molecules from CO gas on the dust grains. So that's it. Thank you very much.